So before I begin with the formal lesson here, I just wanted to ask you a few questions. So how many of you are studying biology? Raise your hand. Quite a few. At least 3 I've seen, right? So tell me, please, tomatoes, what sort of object is it? What sort of, is it fruit? Is it vegetable? It's a fruit. Good. Tomatoes are fruits. All right, so the next question I have is, and that has to do with why I'm so grumpy, right? I mean, when I'm grumpy, I don't sleep too well. Why don't I sleep well? It's because of one very important question. No. In mathematics, we sleep. Although sometimes we have nightmares. Yeah, but my question is birds. So what are they? What is their class? Are they mammals?
Yeah. Wait, no. Do you want to put them like in a domain kind of thing, like a taxonomy?
Okay, taxonomy. What would you say birds are?
They're in the domain of eukarya.
Eukarya. Well, eukaryotes. Specifically, what is a mammal? How do you tell if something is a mammal or not? What do you do? You're studying biology, some of you.
We haven't gone up to yet.
Mammals named because they have mammary glands, so they're animals that breastfeed.
Okay, animals that breastfeed. So then again, I ask you, are birds mammals?
No.
And that's because you believe they don't breastfeed, correct?
Correct.
So that means that birds don't have milk, correct? So let me then present the following video for you as an explanation.
It's well known to all persons of keen perception that birds are in fact mammals. The milk these animals so diligently produce is often squandered on the pavement. And it took the entrepreneurial spirit of some Eastern European denizens, which could only arise from the resigned indifference brought on by harsh, cold climates, to first attempt the milking of an ornithoid. The most successful of those early attempts were on the columbiform, or pigeon. It is speculated that the first established bird milkery was located on the outskirts of the small village of Nova Squashava. Here is the earliest known photograph of a bird milk processing facility in Glova Bravsk. Skipping ahead several centuries, we arrive at a crucial point in our story, where immigrants of Polish and Belarusian descent carried over their traditions into New York, specifically Brooklyn, and even more specifically, the intersection of 13th Avenue and Day Hill Road, where remains the factory to this very day, on the second floor of a paper mill processing facility.
Well,
That's not real.
so one of my important duties is, in fact, as a night job, is to milk birds. What I do is I just have a bird and I just milk it. And what you're going to do is you're going to now eat bird's milk, which I have here. Okay? Am I joking? Do I ever look like I'm joking? No? All jokes died with me a very long time ago. So when you pick this, well, pick one or two, make sure you're not allergic to bird milk, and before you open it, look at the wrapping, please.
It's really good, yeah. It's really good.
Excuse me,
Let's see. This is pretty good for a milk.
It is pretty good.
The chocolate is just masking what's the inside, right? So when you look at it, you can see on the side, you can see a drawing of a bird. So that's what you know. And if you can read Russian, you know what it says. What?
I had something like this before.
So you know the fruits of my labor, right?
Yeah, sure.
Thank you.
Yes.
Did the tests that were given out last time?
I forgot to bring them with me. But yes, I brought them.
Alzheimer's? Can I check?
I brought them last time, so that's the problem. I forgot to put them in the back when I was exiting.
By chance, I have a list of the grades?
Not with me, but if you email me, I'll tell you what you got.
Yeah, just giving us a Russian candy. Birds don't sing.
No? All right, so again, make sure that you see the wrapping. You can see the thing that's on the side. That's at least some evidence. All right, so let's go back to mathematics. So you don't believe me that it says bird's milk? Is that the issue? You don't believe me?
Did you make that video?
Did I make this video? All right, so let's recall what we did last time. So what is the derivative of ln x? Do you remember? Here you go. You missed the presentation, but no, it's bird's milk. What's the derivative of log ln of x?
Log.
ln.
So if I want to find this one, let's recall what we need to do. What is ln of x? So ln of x is the same as log base e of x, okay? So if we don't know how to take the derivative of something, last lesson, one thing that we can do is this thing. Y equals to ln of x. Then what? That implies that e to the y is equal to e to the power of ln x. What's e to the power of ln x? Simplifies to x. And now we can use implicit differentiation. So that implies that if I take the derivative of e to the y, now notice there is a relationship. Y is a function of x. So that's why in this case I cannot say it's 0. Remember I tricked you before and I said it's 0? That's not the case here. So what we have here is that derivative of e to the y is what? E to the y, very well, times y prime, and that's equal to 1. So then I solve, and I see that y prime is the derivative of the function I'm seeking. It's the same as 1 divided by e to the power of y, which is possible to simplify. Yes, it's 1 divided by e to the power of ln x. Now remember what ln x is. It's just in a way a tricky way of pretending that we solved this problem of what power must e be raised to get x. So if I raise e to the power of ln x, I just get x. And we are done. All right? How do I take the derivative of a to the power of x, where a is not necessarily the number e? A could be 2, 3, 5, pi. How do I take the derivative of that? Okay?
A to the x.
No, it is not. Be very careful, guys. Right? Anything that is based on guessing can lead you to mistakes. Right, so we have a to the, we don't need to use y. A to the x is equal to
A log of like as the
power of log.
yeah the
To
power of log
log.
to the power of log.
Yes.
well. You don't like to see a here. You would like to see here e. Knowing that you want to see here e, just put it here. Wishful thinking e. Then what must be here? Then this must be ln. Now it's now what you were saying would be right. Now it's ln a to the x. Okay? What's that? Now I can take and use the property of logarithms, which I don't know, should I review them? You're supposed to know them. So it's e to the power of x ln a. Now in this form I can take the derivative. So then that means that d dx of a to the x is the same as d dx e x ln a. Which is what?
E time e to the x ln a times the derivative of ln x ln a.
Which is ln a. So the derivative of the power is just x times a number. So the derivative of that power is just ln a. ln a will be just like a number, like 5, like 7. Now we can simplify it slightly more. I can take this x and I can move it back up. So this is the same as e ln of a to the power of x, which is simply a to the x times ln a. Okay, next example. How do we take the derivative, and try doing it on your own now, of log base a of x? So we just figured out to take derivative of a general logarithm, of the natural logarithm, and now we want to figure the derivative of a general logarithm. So what's the idea? How do we approach this? How do we approach it? One, we can say y equal to log base a of x. Then what? We know how to take derivatives of a to the y. So we raise everything to the power of the logarithm. What do we get here? a to the y is equal to a to the power of log base a of x, and it equals to you don't want to tell me, or you don't know? Don't know. All right. Then I guess again we have to review logarithms. This is a to the power of log base a of x is equal to x. The derivative of that is what? Derivative of a to the y is a to the y ln a times y prime. Wonderful. So that means that y prime is equal to 1 over a to the power of y ln a. Now a to the power of y is simply x. 1 over x ln a. All right, review of logarithms. Very brief review of logarithms. So I mentioned already before that if I, for example, try to solve the equation 2 to the x is equal to 1, then you can give me very definite answer, x equals to what number? 0. I'm scared to ask the question, do you understand why 2 to the 0 is equal to 1? So I'm not going to ask it. What's 2 to the 1? Or 2 to the x equal to 2 means x equals to 1. If I have 2 to the power of x is equal to 1/4. What's x then? -2. So for some values you can give me a solution x, and for other values, like for example if I have 2 to the x equal to 3, then x equals to what? Well, the best way to answer it is it equals to log base 2 of 3. What this means is that the power that 2 needs to be raised by to get 3. That's just mathematics talk. So it's just like a label. So in general, if I have 2 to the x equals y, what is x equal to? Log base 2 of y. So in essence, you are not solving. This is actually something that you're very familiar with. Root of 2 is not a solution to the problem x squared equals to 2. It's not a solution. It's just naming it. It's just referring it by word. Okay? This is similar to let's say solving the equation x squared minus 2 equals 0. So you would say that x equals to root of 2. But root of 2 is not quite a solution. It's just labeling it. It's saying it's the number that when squared gives you 2. Okay? Similarly, for logarithms, what you do is the number when placed over the power 2. So placed over 2 in its power, it will give you the whatever value you want. So that tautologically means that 2 to the power of log base 2 of 10 is what? 10. Okay? Now, there is a lot of work in understanding this function. Just why do you believe it exists? Why is there's so many whys? For us, for a moment, what's important is to understand some properties of logarithms. So property 1 of logarithms is that log base a of a product of two numbers of m times n. This happens to be the same as log base a of m plus log base a of n. We have log base a of m divided by n is log base a of m minus log base a of n. So those are things that you should know from pre-calculus. And honestly, they're not too hard to know at all, if you want to. Log base a of a number of the form m to the power of b would be b log a of m. Those are the three properties that we need. So in logarithmic differentiation, this is a technique that helps you solve derivatives of very complicated functions. So for example, suppose that what you have is a function of the form f of x, and that's equal to x squared times x cubed minus 1 to the power of, or maybe root of that, divided by sine x, and on the denominator we have also x squared plus x minus 1 cubed. And imagine that this function, you were asked to take the derivative for it. So if you look at this function f of x, it's of the form x squared, x cubed minus 1 to the power of 1/2 divided by sine x, x squared plus x minus 1 cubed. Now we can apply a bunch of product laws, a bunch of quotient laws and whatnot, and solve it this way. But there is a much simpler way of approaching this problem. Observe what happens if I take first ln of fx. I apply logarithm. That is ln of x squared x cubed minus 1 to the power of 1/2 divided by sine x, x squared plus x minus 1 cubed. Now by appealing to properties 1, 2, and 3, I can break it down. So first of all, there is top divided by bottom. So this is ln of x squared times x cubed minus 1 to the power of 1/2 minus ln of sine x times x squared plus x minus 1 cubed. Okay? I appealed to property number 2 of logarithms. Now, I can break it much further because now this is a product and this is a product. So, by applying laws number 1 and 3, I can write it as 2 ln of x plus 1/2 ln of x cubed minus 1 minus ln of sine x, and because there is a minus in front of it, it's going to be minus 3 ln x squared plus x minus 1. Do you see? So now I can take the derivative. Now the derivative of this expression here, so if I take derivative of ln of f of x, what I get is 1 over f of x, that's the derivative of a logarithm, times f prime fx. And this is what I'm going to try to solve for. That's going to be equal to the derivative of 2 times ln x, which is 2 over x, plus the derivative of this expression, it's going to be 1/2 x cubed minus 1, 3x squared, minus derivative of ln of sine x is going to be sine x on the bottom. Derivative of sine is cosine, minus 3 derivative of logarithm of x squared plus x minus 1. It's going to be on the bottom x squared plus x minus 1. Derivative of this function is 2x plus 1. What do we do next? Yep.
Never mind. I have a question.
Guys, don't put your head in the sand. You see, I mean, you tell me if you understand something or not. If you don't understand logarithms, I have to go over that. This will be pretty terrible. I mean, we need to cover a lot of material.
What is, what are you doing? Like, why is there the 2x plus 1 over x squared plus x minus 1? What rule are you using?
How do I differentiate logarithms? So if I take derivative of ln of anything, that will be 1 over that anything times the derivative of the anything. I'm using chain rule.
Oh, right.
So my goal is to figure out, you see what I did? So you could have faced this derivative, just do it using product law and quotient law, and it will be pretty messy. Or you can do this. This is easier. Okay? So finally, I have everything ready. So all I need to do is multiply this expression that I obtained by f of x by the original function, and I'm done. So that means that f prime of x is simply going to be my original function x squared times x cubed minus 1 to the 1/2 power divided by sine x squared plus x minus 1 cubed times what we have in parentheses, 2 divided by x, plus 1/2 3x over x squared, 3x over x cubed, sorry, minus 1 minus cosine x divided by sine x minus 3, 2x plus 1 over x squared minus x squared plus x minus 1. Close brackets. Let's begin simpler. What's the derivative of ln of sine x?
Why did we multiply by f of x?
Because our goal was to take the derivative of this function. So what I did is I simplified some arithmetic by first applying logarithm to this function and using the properties of logarithms to make it no longer quotient law, no longer product law. I simplified it. So you can try, do this question directly. You can solve this question directly, see if you will be successful. Or you can apply the logarithmic technique.
So when you apply ln of the function, wouldn't it be 1 over the function and then times the derivative? But you
But then I didn't simplify anything. If I take the derivative directly without using the properties, it will be 1 over times the derivative of this function. But that is what I'm trying to find, the derivative of this function. So that would not help. You agree? 1 over, and then back to the problem 1, back to the same situation. So what I do is I apply logarithms because I know it has properties.
Yeah.
It can do this.
So that whole thing is just finding derivative.
Yes. So this whole thing is to find the derivative.
But for the derivative, you didn't switch. You didn't put sine x times x squared plus x minus 1 on the top, the numerator.
No, I mean what I did is I brought it down to the situation. This is basically identity in terms of I used 1, 2, and 3 for logarithms, and I was able to break it down like this. Okay? And then you take the derivative, and then the derivative of this function by chain rule is going to be, it's implicit differentiation. You say, I'm saying 1 over f of x times the derivative of this function is equal to all that stuff. So all I need to do is multiply both sides by f of x by the original function, and I get I just get on this side of the equation just f prime. Okay? Now again, I mean, you see, one thing that bothers me is, I mean, you look at it, the logarithm, derivative. This is somewhat of a boring and just technical question. But what are logarithms? If you just look at the function 1 over x, in architecture, it would be if you take, if you stack, what do you call them? If you stack bricks one on top of another, and you want to create a building that is leaning forward. You see, what's going to be the maximal lean? It's going to be related to the function 1 over x, to the derivative of the logarithm. Okay? So if you want to know what's going to be the curve, that curve is related to the derivative of the logarithm. There is a paradox that it's pretty interesting. If you take the most common word, I think, right? Visos did something like this. That if you take the most common word in the English language, and then consider next to it the next most common word, right? The relationship is going to be 1 to 1. This is 1. The next will be 1/2 as frequent. Next is going to be 1/3 as frequent. Next is going to be 1/4 as frequent, right? So it's all those things are all very related. What's 1 over x? 1 over x is the only formula. Look at it. If you look at x to the power of -1, right? Well, actually, this has to do with antiderivative. So if you got the derivative equal to x squared, or let's say x squared, then the original function that you took the derivative from was something like x cubed times 1/3. you can do this, you can just guess very easily, except for x to the minus 1. That's an exceptional thing. Okay? So there is something very special about 1 over x. There's something very special about logarithms. All those things you can begin understanding if you think about them. This, of course, is just like a just technical question in a sense, right? But what is more interesting is to understand why property 1, why property 2, why property 3 holds. Anyhow, can you solve this question? So what's the derivative of this function? So what you have is 1 over sine x, and by chain rule times cosine x, okay?
Why does 3? You just mentioned like why I don't understand how 3 works. Like that doesn't seem like it would.
Why 3 works?
Yeah.
Okay. Let's see. Why all of them work. So think of log base a of x as saying trace me over a and get x. That's what this is saying. So let's first ask, is there something like this? So this is going to be a number. So maybe it's saying I'm a number, and if you place me over a, you get x. Okay? So let's first see what this is. Log base 2 of 4. Can you tell me what it is? 2. You can guess. 2. That was a guess. You agree? Basically, this is a riddle. In general, you're not able to answer this riddle, but sometimes you can just say and guess. Okay. What about log base 2 of minus 1? What is that going to be? I just want you to get a sense of what those things are.
Negative 0.
Negative. Right, that's good. Right? Get a sense of what those things are. Can you tell me? So this is saying place something over 2 and get minus 1. And this something is, for our purposes, a real number. Is there something that you can place over 2 and get a negative number? No. So this is undefined. Does not exist. Okay? So in particular, domain is x has to be bigger than 0. Okay, so this will not ever work if x is not bigger than 0. Now, I mean, I can spend 5 lectures explaining logarithms. That's a very, very difficult thing. In real analysis, the first thing you do is, when you do calculus truly, not like we do it, right? You first have to explain what those objects are. Why do they exist? How do I know that there is a number? I mean, I might not know what the number, but do I know what it is? Funny enough is that if you believe that there is such a thing, you will be able to compute it. You understand? Just by belief alone, if you believe there is an object that exists that works like this, you will be able to figure out what its values are. That has to do with okay. So for example, your calculator can do something like this, which I can actually teach you why it works. So if I take ln of 1 plus x, and I take its derivative, that would be 1 over 1 plus x, correct? If this object means anything, its derivative is 1 over 1 plus x. Now, 1 over 1 plus x can be written as 1 minus x plus x squared minus x cubed plus x to the power of 4 minus x to the power of 5, and so on, and so on, forever. That's the pattern. Okay? So it can be written as an infinite polynomial. Now, that means that ln of 1 plus x is going to be the same as x minus 1/2 x squared plus 1/3 x cubed minus 1/4 x to the power of 4 plus 1/5 x to the power of 5, and so on. And so on and so forth. So by taking just a chunk of it, let's say, you can estimate what logarithm is doing. Okay? I'm not explaining why this works, but just the idea is that if you believe that something works, something exists, you can actually figure what it is. And this is related to sum of the numbers 1 over. So 1, 1/2, 1/3, etc. Summing this 1 over x series. So next. So in terms of the properties, what can we right away quickly see about logarithms? So if I have a to the power of x plus y, this is the same as a to the power of x times a to the power of y. You agree? So the implication is, if I have a to the power of log base a of m times n, what do I get?
Do you want the derivative?
No. I just want people to understand why property 1, 2, and 3 work. So what is a to the power of log base a of m times n? It's just from here. Very good. It's mn. Just basic tautology. Okay. Again, I mean, I might have bewildered you. I just said this, right? Forget it. Erase it from your mind. Right? My point was only what? If you believe in something, you can figure out what it is. Okay? If you just believe that there is an object that behaves this way, you can figure out how to calculate it if you think about it. Okay? But the very first ideas will be, okay, so if this object exists, how does it behave? So it behaves that if you place it over a, that's all you know about it. You get whatever is the value. So if it's a raised to the power of log base a of x, you get x. So it's m times n. Now, if the number m can be attained, m is going to be the same as a raised to the power of log base a of m, correct? That's m. Now n is a to the power of log base a of n. Now if I multiply them together, I get a to the power of log base a of m plus log base a of n. And I verified this property. I verified property number 1. By similar procedures, I can verify property number 2 and 3. I see that this is what should hold. Okay? That's what you should have been doing in pre-calculus. Now, okay? Figure out the derivative of this thing. What's the first thing that we do here?
Do 1 over that.
No. That's why we have 1, 2, 3. We don't want to apply derivatives right away. We want to use the logarithmic properties to simplify the derivative. Yes, please?
So you start with natural log of x plus 1 minus the natural log of the square root of x minus 2.
Wonderful. And then we do it a bit faster. So that would be ln of x plus 1 minus 1/2 ln of x minus 2. The derivative of the first guy is simply 1 over x plus 1 minus derivative of the second guy is 1/2 1 over x minus 2. Next example, we've seen how to take the derivatives of 5 to the x. Derivative of 5 to the x would have been 5x ln of 5, sorry. On the other hand, the derivative of x to the power of 5 would have been 5x to the power of 4. Correct? So this is 5 to the x, this is x to the 5, very different functions, very different expression. Now I want you to find the derivative of x to the power of x. Hint is just set y equal to x to the x, and then take ln of y equal to ln of x to the x, because logarithms can simplify calculation. So what do I do here? You move the x to the front. And then you find the derivative of both sides. Derivative on this side is 1 over y times y prime. Y prime is what we are searching for, correct? Is equal to the derivative of x ln x. It's going to be, what law are we going to use here?
It's going to be x times 1 over x.
All right, so we can differentiate it as x times 1 over x
That's x.
plus plus ln x. I prefer to, just maybe the way I prefer it is you first take the derivative. So you take the derivative of x and you get ln x plus x times the derivative of the other function. It's product rule. Right? This is a product here.
So why is the derivative of that ln x?
Why is the derivative of, well, what we do is product rule. It's x, one function that we know how to differentiate, times another function that we know how to differentiate. So here I take the derivative of x, leave the other function intact.
Okay.
That's product rule, right? So,
Okay.
so I just have this derivative travels from x to ln. So here it is applying to x, here it applies to ln. So this is ln x plus 1. So therefore y prime is simply y times ln x plus 1, which is, what's y? Y is x to the x. Okay? Next example. What's the derivative of that? So do you know what's the derivative of this?
0.
Good. There is no dependency on x here, so that would be 0. Next example, tell me what's the derivative of x to the power of root x. So what do? We set y equal to x to the root x. Then we can apply logarithms. So ln of y is ln of x to the root x. So you see why we apply logarithms is because logarithms allow us to drop the power down. So that allows us to carry the power down. Ln of y is root x ln x. Next, we take the derivative. So the derivative of ln of y is what? 1 over y prime. This equals to what? 1 over 2 root x ln x, yes? Root x divided by x. So then I just multiply everything by y. So y prime, the derivative of this function is simply x times x to the power of root of x times 1 over 2 root x ln x plus root x over x. Estimating the number e. So observe that 1 is equal to the derivative of the logarithm where x is equal to 1. Correct? The derivative of the logarithm will be 1 over x. If x is equal to 1, it's 1 over 1, it's 1. So, but by definition, this is limit as h goes to 0 of ln of 1 plus h minus ln of 1 divided by h. Now, ln of 1 is equal to what? 0. So this guy here is 0. So what we get is limit as h goes to 0, ln of 1 plus h divided by h. Limit as h goes to 0 of 1 over h, ln of 1 plus h. And I can now take this 1 over h and I can place it in the power. So that's what 1 is equal to. So then if I put everything to, I can get rid of the logarithm if I raise everything to the power of e. So that means e to the power of 1 is equal to e to the power of limit where h goes to 0, ln of 1 plus h to the 1 over h, which equals simply the ln cancels. So that's equal to limit where h goes to 0 of 1 plus h to the power of 1 over h. Which means if I see 1 plus something that vanishes to 0 raised to the reciprocal, I get e. So what happens if I do this? Limit where h goes to 0 of 1 plus 5h raised to the 1 over h. So it's like a question I asked you for exam 1. What would you like to see there? What would you like changed?
You want it to be 5h, or 5 to the 5 over.
Yeah, so you wanted 1 over 5h. Now I introduce the 5. I have to cancel it, so therefore it is. So to cancel it, I can say, well, maybe I won't put the parentheses just right away. I'll just put 5 here. Okay. Now 5 crosses out. It's exactly the same expression. So this is limit as h goes to 0. 1 plus 5h to the power of 1 over 5h raised to the power of 5. So that gives you what? You see what I did? I just took this 5 and I factored it out. So the guy inside of the square brackets is what?
Would it be 5e since you factor up the 5, you have to put it back?
So it would be, so this 5, I factored it from the power. So this would be e raised to the power 5. Because the guy inside of the square brackets, let's just do it slower, it's e, and I have the power 5 outside. So this means e to the power of 5.
Can I ask why you would do that, like all of that? Is this a method for something in particular, or is this like an alternate way to?
Well, this gives you a very important limit. It tells you how to find. We're skipping one chapter because we don't have time for it. But for example, if you see something like 1 plus h to the power of 1 over h, that tells you that's the number e. So for example, when you go into your bank, right? So you have compound interest. So the amount of money that you have in your bank is, let's say you put $100. So $100 times 1 plus a fraction, plus h is going to be that fraction. Okay, so that means how much it grows. So let's say your h is, it grows by a small fraction, let's say 0.05. That's probably quite a lot. But so 0.05, 5% growth in 1 year. Okay, so the next year, it's going to be 101 plus h squared, and onwards, right? Now, if you this is actually I don't see that I can answer it without going into details. So I'm just hesitating. Should I go to the details? Should I not go into the details?
But essentially, this is.
I mean, everything that we write here has many, many deep applications, right? But to even mention one of them, it requires a lot of talking. It requires me to say quite a lot of things. Okay. So maybe what I'll say is this, right? So if when you look at those limits, they can have many meanings. So one immediate meaning is exponential growth and decay.
Okay.
So actually, if you look into chapter 3.7, you see rates of change in natural and social sciences, and you will see examples where this limit comes in handy. This also comes in handy when you approximate the binomial theorem. So pretty much, let's say if you open a book and you want to know what's the number of errors on a given page, it's going to have a distribution that's related to E. How is it going to relate to this E? It's going to relate to this E because in relative to this formula. You understand? You're going to notice that it's related to E if you understand this limit. Because you see, a lot of things in life are either existence or non-existence, right? On, off, on, off, on, off. So when you look at mistakes in your page, correct means 1, error means 0. Okay? So it's binary. Now binary is success or failure. It's random. So something is switched randomly on or off with some probability. So that will actually, you can translate it into an equation that would basically, you would see this limit inside of it. Not quite this limit, but a variation of this limit. Maybe something like this you will see. You understand? And then with this information, you are able to approximate the binomial. It's called, if you are interested, what I'm talking about is called Poisson distribution. And this occurs very frequently because almost everything is either success or failure, or either existence or non-existence, on or off. Okay? And then you would see this limit. You would see this limit when you consider exponential growth or decay, which I kind of said, but I didn't want to go into because there is basically continuously compounded interest, or there is discretely compounded interest, all that stuff. Okay? So you would see those limits. So everything I'm saying, I mean, even if it's the most boring thing for the moment, it's very deeply interesting. But for that, it takes a lot of time. In a way, there is no point to anything I say at all. I mean, because if it's not going to be continued later on, if you're not majoring in mathematics, who knows? That's definitely how you feel. I mean, you feel. So you should look into chapter 3.8. You can see a lot of applications, but we'll skip it.
3.8 or 3.8?
Both of them actually, but 3.8 in particular. If you look into the last pages, you see the same limit. In fact,
What page is it?
in my book it's 242, but it's basically 3.8. Okay. So everything I'm saying, I can show you a bit. You will space out immediately. I can show you. I can show you. Let's say the capstan example. You would see. So that's when I mentioned the rope and the motorcycle, right? So you're pulling this way, and the motorcycle is pulling this way. In this formula, you will recognize both trigonometry because of the circle. There will be trigonometry for the tension in the rope, and there will be the exponential map. So it comes out all the time. When you are simulating a spring. How this is going to move. So the spring is going to actually move. The solution will involve something like this. It would be lambda I plus e to the minus lambda I, where I is root of minus 1. That would be, so this would be some A, this would be some B. That would be a solution of the moving spring. And pretty much anything is modeled by a spring, right? Almost any force it's just approximated by a spring. Let's talk a little bit about related rates. So suppose that what you are seeing is a video where there is a ship, and the ship is leaking oil. So what quantities change as a function of time in this video? So you see what I'm trying to say. So it's going to be a very, very basic, very simple video. And what you're seeing is that there is no turbulence in the water. And the ship has a hole and it's leaking oil. And the oil is always circular. But what do you think will be changing as a function of time? You were saying something then.
Yeah, so the volume of oil in the ship.
OK, so it's two-dimensional, so the area, right? So we can say area is really a function of time. What else is a function of time? The radius. So the radius is a function of time. What else is a function of time? Anything, any other quantity that you can see? The what?
The change of time.
Well, yes, but that's just a time bar. That's outside of the video. So if you just look at the video, what is a function of time in this video? The what? The circumference. Wonderful, right? And maybe other things. The diameter, correct. And who knows what else, right? So a bunch of things are just really something that you can observe is related to time. Now, why are they called related rates? They're called related rates because, for example, the area is always, regarding, just I can suppress time, area is always the same as the area of a circle. And the area of a circle is pi r squared. So you see that although r can be thought of independently as a function of time, and area can be thought of independently as a function of time, I can suppress time, and I can see that there is a relationship between a, the variable a, and the variable r. Correct? Now, I also know that there is a relationship between the diameter and area. So for example, area can be written as pi diameter over 2 squared. So there is also a relationship between A and diameter. There is a relationship between R and the circumference, right? So the circumference is twice times pi times R. I can also relate area and circumference. So for example, area is pi times circumference divided by 2 pi squared, for example, right? So all those quantities are interrelated. I can put a formula involving one variable and another variable. So a most basic application of calculus is that to related rates. So suppose, for example, if the radius has the following property, dr dt, or let's actually, it's more natural to say, suppose that we know that the A dt is 2 cubic meters per minute. So square meters, not cubic meters. Square meters per minute. Find the RDT. So first of all, notice that the ADT is 2 cubic meters per minute. What does it mean? Notice there is a positive number, so it's 2. What does it mean? It means if I press play and wait for 1 minute, the area in that 1 minute will do what? Will grow by extra 2 meters squared. Okay, so the area will add 2 meters. So if I wait 3 minutes, I will grow the area by 6 meters. So when I ask for the RDT, I'm asking how quickly is the radius growing. Now, before you even solve it using any mathematics, what's your impression? Is the radius going to slow down in speed, or is the radius going to increase in speed? So find the RDT when A is equal to 4 meters squared, let's say. So the question is first, is the radius gonna slow down in its increase, or speed up, or what? What do you think? So you know that for all the time the leaking is constant. It's basically at the same rate of 2 meters squared, anywhere in the video. What can you say about the growth rate of the radius? It says it remains the same. Look at the formula. It's pi r squared. So one person said speed up. How many agree that it will speed up? One person. That's it.
What's the question?
My question is, what happens to the rate of change of the radius? So if you watch this video, you know that the leak, so you see, I just told you that the leak is 2 meters squared per minute. So if you watch this video, you know how the area grows, right? You see what's going to happen in this video. You're going to see a small circle that is growing. I'm asking what's going to happen to the radius. Is it going to grow at constant rate? Is it going to grow faster and faster and faster? Is it go slower? What is your impression? How is the radius going to grow in this video? So you're watching this video, the radius, right? Here is what it means to grow faster and faster and faster. So it goes like this.
Wouldn't it be consistent with the growth of the area?
So you're saying this constant.
Yeah.
Okay, so that's my question. Do you understand my question, first of all, right? So I'm first of all asking how is the radius going to grow? I want your intuition. All right, so raise your hand if you say that radius is going to speed up. One person. So the radius is going to be faster and faster as I watch this video. So that means that If this is the ship, the radius is going to do this. Right? Now raise your hand if you believe the radius is going to grow at a constant rate. It's always going to be just like the ADT is always, for any moment of time, it's the same. So the radius is going to just grow steadily. 1, 2, 3, 4. Anybody now believes that the radius is going to slow down in its growth? It's going to grow slower and slower and slower. 1, 2, 3, 4. The correct answer is that the radius will have to slow down, because if I add 2 units to the radius, by how much is the area going to grow?
The same amount.
No, if r is increased by 2, it grows by over 4 units. Over, right? It's going to grow by more than 4 units. If you do this, if you change r to r plus 2, area will be changed to area. Well, you see, so how should I write it? So we have pi r squared is going to be changed into pi r plus 2 squared, which is more than pi r squared plus pi 2 squared. So it's going to grow quite a lot. Now, here is how we solve such question. So we are going to set a equal to pi r squared. And then what we are going to take is we're going to take the derivative with respect to time. So we're going to calculate the a dt. This changes as a function of time, and that's going to be equal to the derivative of pi r squared as a function of time. What's that going to be? So what's the derivative of pi r squared? The best we can do. Now r is a function of time. So that would be pi times 2r times what? You see that if I knew the exact formula for area, and I knew the exact formula for r, that would not be any difficulty finding the derivative dr dt. But what I have is I have this relationship, and this is just a function of time equal to pi times another function of time squared. So by using implicit differentiation, this is pi times 2r times what? Times dr dt. That's dr prime. That's what we're searching for. Now, the ADT is equal to 2. So we have 2 is equal to pi times 2r dr dt. So that implies that our dr dt is equal to 2 divided by 2 pi r, correct? So now observe what this is telling us. The r dt is 1 over pi r. So notice that the bigger the r, the smaller is the rate of growth. You see, the bigger the r, the smaller is the rate of growth. Exactly, the rate of growth is inversely proportional to the size of the radius. That's what this equation is telling us. See? This is telling us that the r dt is proportional to 1 over r. So if I grow the radius to twice the size, the rate of growth is going to be twice as slow. Do you see that? That's what you can read from this equation. Now, we know that a is equal to 4, right? I asked you to find it when a happens to be equal to 4. So somewhere at some moment of time, I grow the radius enough so that the area is equal to 4. So 4 equal to pi r squared. So r is going to be equal to 4 over pi square root, which is 2 over root pi. So that's what I will substitute in here. So the r dt is 1 over pi 2 over root of pi. Which is simply 1 over root of pi times 2. I don't think I have time for more examples. We'll continue doing this on Tuesday. Have a good day.